Yeah, so I guess the question now is what's the efficiency for the minimax minimax search? Well, minimax, as we look at as the way we saw it in the toy example, it's basically a exhaustive depth first search. So that's why it will give us the time and space capacity uh, of a depth first search algorithm. So for example, for chess, when the branching factor is 35 and the number of the maximum depth is probably 100, um, you know that number is going to get very, very big. And exact solution is basically infeasible with modern computers. So, but then the question is, do we really need to explore the whole tree? Or can we just, search in the neighborhood of our current state and get just as good results?
Yeah, so given the resource limits, we want to do something that can help us speed up our computation. One idea is to prune the game tree. And here's an example to motivate it. So let's consider the previous toy example.
If you look at the tree, we first saw 3, 12, and 8, right? So we know that the value for this first node here is going to be 3. And then when we look at, the second successors, we see this value 2. The thing is, I mean, it is possible that, there are, values that's less than 2 in, it's in the following successors for this minimizer. But the thing is, since the maximizer already have a value 3 on its hand, like we know that, and we have the value 2 here for this first successors, we know that whatever this node return is going to be smaller than or equal to 2. And that's why we technically don't even need to explore, these 2 branches, because whatever value that's returned here will not affect the value of our root node, which is what we care about, or I guess the set of action that's picked by the root node. So like we can rewrite it out. I mean, these happen to be bigger than 2, so they're not picked anyway. And I guess similar things can happen, but here we actually can't actually prune anything because 14 and 5 are actually both bigger than 3. But we can actually prune this too.
Okay, now let's further motivate why we might need alpha beta pruning. So let's say you're at, this is the min node, the max node is symmetric. So let's say you're at node n, you're trying to calculate the value for this node n here. So we're looping over n's children, and n's estimate of the children is dropping because we are trying to minimize the value, and the v value at node n is going to be smaller and smaller. And who cares about node n, that value there? Is the maximizer somewhere like along the line somewhere on the path to the root, right? So if you focus on that maximizer right now, let A be the best value that the maximizer has seen so far. And if n becomes worse than A, that maximizer is not going to care about the rest of n's children, because it's never going to pick the path that goes to n. And therefore, we can just short circuit there as soon as n has found a value that's less than A. And that's how we can just prune the rest of the sub-branch that n has. And that's basically similar to the toy example Masood talked about earlier. It's just more formalized reason of why we do alpha beta pruning. And next, let's go over alpha beta implementation. So that alpha becomes represents the max best option from path to root, and beta becomes the min's best option on path to root. So instead of just updating the v along during the calculation, you will check whether the value v is greater than the beta value at the max node. And if it is, you're going to terminate immediately. So when it says if v is greater than or equal to beta, return v, it means I'm going to stop exploring any of my all the rest of my successors, and I'm just going to return the current v value that I have. It means if v value is greater than or equal to the beta value, I'm going to short circuit here and save computation.
Yeah, and I guess just to elaborate on that, why can you short circuit there?
And that's because beta represents min's best option on path to root. And if the value that the max node has already is greater than the min's best option, it means that min's basically not going to pick this max node. And thus, it's not going to care about what v is. So basically, we can just short circuit there and call it a day. And last but not the least, there's the line below return v. That's basically doing the job on the maximizer side to update its best option on the path to root, so that when it calls the minimizer will compare its v to the alpha that the maximizer updated, and then prune the other way.
All right. So you might ask, when we have this short circuiting and returning early, wouldn't that affect the value of some parts of the tree? Because we're not, we're trying to save computation by not going all the way through. I think the actual answer is that it actually doesn't affect the value of the root node, but it does affect the value of some intermediate nodes. So basically, if you look at this particular example, the minimizer will short circuit after seeing the 10 here, because it knows that you can't actually get any values that will be returned upwards. So basically, it will just return 10 at this minimizer node. But we know that the actual value for this minimizer node is 0. But the thing is, because this doesn't affect the root value anyway, so like having the wrong value here actually doesn't negatively affect the values at the root.
Yeah, exactly.
So basically, the other thing to note is that good child ordering does improve efficiency, because if you, let's say, put the values that's more likely to cause a short circuit earlier, could save, could help the node terminate earlier instead of, going all the way across all the children's, and in the last children realize, actually none of the other children's matters.